Some 138 billion years ago, the entirety of existence, all that has been and all that will be, burst forth from a singularity more minuscule than a single grain of sand. Yet what is truly staggering is the journey we are about to undertake into the impossible domain that preceded that cataclysmic moment. This is a place where nothing was not an empty void, where the passage of time had no meaning, and where the very idea of being dissolves into paradox. We will delve into a quantum froth seething with phantom particles, clashing multiverses without number, and mathematical planes of existence that dwarf our own cosmos. If you're prepared to challenge the foundations of what you perceive as real, then let us begin. Imagine the absolute final moment, the literal boundary between the concept of before and the dawn of after. Physicists label this T equals zero, a simple name that belies the most ferocious transformation in the universe's history. At this frontier, any notion of a preceding era becomes nonsensical, as time itself had not yet begun to flow. Consider that for a moment. No clocks ticking, no process of aging, no chain of cause and effect. It was not a darkness awaiting the arrival of light, but a total lack of duration itself. Here, our mathematics falter, like a computer commanded to perform an impossible calculation. The equations of Einstein, which so elegantly map out gravity and space-time everywhere else, cease to function. They yield only infinities and contradictions, as though reality has posted a do not enter sign written in the very language of physics. The mystery deepens, however, because the instant we are trying to comprehend is not merely the start of our universe. It is the genesis of the very scaffold upon which beginnings can occur. Prior to this point, there was no stage for any cosmic play to be performed. There were no dimensions to traverse, no space to occupy, no time to elapse. Attempting to describe what came before the Big Bang is like trying to explain the color of an object that has never encountered light in a realm where light cannot exist. We are forced to use ideas that are only valid after the event we seek to understand. And yet, contemporary physics hints that something extraordinary was occurring in this inconceivable state. Quantum mechanics reveals that even in a perfect void, flashes of energy can momentarily emerge from nothingness before vanishing once more. These quantum fluctuations are happening constantly in the vacuum of our space today. If they could also transpire in absolute nothingness, then perhaps that nothing was never truly empty. The prevailing hypothesis posits that our whole cosmos originated as one of these quantum flickers. But this one, instead of disappearing, ballooned in less than a trillionth of a trillionth of a trillionth of a second. This microscopic bubble of potential expanded faster than the speed of light, fabricating the very fabric of space as it grew. Consider it like a perfect crystal forming in a solution that does not exist. The solution itself is not there. The medium is absent. Yet somehow, the crystal generates both as it expands. That crystal becomes the entire vessel, the entire world, the entire reality. This mechanism, known as cosmic inflation, accounts for why our cosmos appears so remarkably consistent in all directions. It also clarifies why the geometry of space seems flat rather than curved. But it forces upon us an even more bewildering question that scientists continue to grapple with. If quantum fluctuations can conjure one universe out of nothing, what would prevent them from doing it again? The mathematics imply they would not cease their work. They point towards something far more spectacular than a single cosmic birth. But what we find as we dig deeper makes our own origin seem almost straightforward. When you believe a container is completely empty, is it truly void of all things? Most would say so, but physics uncovers a startling truth. What we perceive as empty space is, in fact, an arena of invisible, ceaseless activity. Even in the deepest vacuum of intergalactic space, where you might find only a single atom in a cubic meter, space itself is vibrant with energy. This is not the abstract nothingness of philosophical debate. This is a form of nothingness that can be measured and proven to be anything but inert. Scientists stumbled upon this when they attempted to cool systems to absolute zero, aiming to drain every last speck of energy. They discovered this was impossible. The energy never falls to zero. Even at the coldest achievable temperature, minus 273 degrees Celsius, quantum fields continue to thrum with what is known as zero-point energy. It is akin to trying to still a simmering pot of water, but regardless of how much you cool it, minuscule bubbles perpetually form and pop at the bottom. These quantum fields pervade every centimeter of the cosmos, creating what is termed the quantum vacuum. Visualize an ocean that appears utterly placid from above, but under the surface, countless microscopic creatures dart about in patterns too swift and small for the eye to perceive. The quantum vacuum behaves similarly, appearing empty while it secretly hosts a constant churn of creation and annihilation on subatomic scales. Here, things become even more peculiar. These fields can borrow energy from the future to spawn pairs of particles, which exist for a fleeting moment before canceling each other out and returning to nothing. This is occurring trillions of times every second in the space all around you. The borrowed energy is repaid so rapidly that the universe's cosmic ledger never registers the loan. Scientists confirm this is not mere theory by observing the Casimir effect. If you place two metallic plates incredibly close together in a vacuum, the quantum fields between them have less freedom to fluctuate than the fields outside. This difference generates a minute but real force that pushes the plates together. So-called empty space can literally exert pressure. But here is the thought that may truly challenge your perspective. If our entire cosmos arose from a quantum fluctuation in a vacuum, what was that vacuum residing in? What was the source of the quantum fields that had the potential to fluctuate to begin with? We are compelled to wonder if even more profound layers of nothingness exist. Some physicists theorize that mathematics itself could be the bedrock beneath all existence. Not numbers on a page, but pure, abstract mathematical relationships that have an independent reality. In this scenario, our universe is composed not of matter and energy, but of mathematical patterns that are so intricate they can become self-aware. Others propose that consciousness has a foundational role, shaping reality through the act of observation. Quantum mechanics demonstrates that particles remain in a haze of multiple states at once until they are measured. Could the very act of observation by a conscious entity collapse infinite potentials into the single universe we perceive? These inquiries guide us toward an even more bizarre possibility regarding what was present before being. Right now, particles are materializing and dematerializing inside your very body. This is not a concept from science fiction. These are virtual particles, and they're essential to the fundamental workings of reality. Every second, quadrillions of these spectral entities flicker into being within your cells, endure for an impossibly short duration, and then vanish as if they were never there. Virtual particles might sound imaginary, but their effects are real and measurable. They are the reason for the magnetic moments of electrons, the interaction of light with matter, and even the powerful force that holds atomic nuclei together. In a universe without virtual particles, atoms would not be stable, chemistry would not occur, and you would not exist. Consider virtual particles as a form of cosmic credit. They borrow energy from the quantum vacuum, use it to exist for a moment, and then repay the loan by disappearing. The more energy they borrow, the shorter their existence. Some virtual particles last for only a 10 millionth of a trillionth of a trillionth of a second, but in that incomprehensibly brief instant, they can wield immense energy. The quantum vacuum is not an empty stage awaiting actors. It is more like a cosmic cauldron where ingredients perpetually dissolve and reform. Virtual photons transmit the electromagnetic force. Virtual gluons are the glue that binds quarks into protons and neutrons. Virtual particles of all kinds are constantly emerging from and returning to the void, constructing an invisible scaffold that supports our visible world. Here is the most astonishing part. These virtual particles can sometimes become real. If enough energy is injected into the quantum vacuum, a virtual particle pair can be forced apart before they have a chance to annihilate, transforming them into permanent members of our reality. This very process occurs at the edge of black holes, where the intense gravity provides the energy to rescue virtual particles from their quantum debt. Stephen Hawking realized that black holes can slowly evaporate by converting virtual particles into real ones. Close to the event horizon, gravity can pull a virtual pair apart. One particle is consumed by the black hole, while its partner escapes into space as tangible radiation. The black hole loses a tiny amount of mass in this transaction, gradually shrinking until it vanishes in a final flash of energy. This mechanism hints at something profound about existence. If virtual particles can be made real with a sufficient energy boost, and if our entire universe might have originated as a quantum fluctuation, then the line separating the real from the virtual becomes remarkably blurred. Some physicists entertain the idea that our whole cosmos might still be, in some sense, a virtual entity, living on energy borrowed from a deeper layer of reality we have yet to discover. In this view, everything we perceive as solid, from planets and people to entire galaxies, is existing on borrowed time within a vast cosmic fluctuation that began 138 billion years ago. But if virtual particles can give rise to our universe, they might be birthing others as well. The very same quantum vacuum that spawns fleeting particles around us could be generating entire cosmoses in realms beyond our detection. The consequences of this thought lead us to a possibility that makes even our own cosmic genesis seem small. Our universe could be just one bubble floating in an endless cosmic ocean. At this very moment, innumerable other versions of you could be experiencing slightly different versions of this narrative in parallel worlds. Some of these universes are almost indistinguishable from ours, perhaps differing only by the location of a single subatomic particle. Others are so alien that their laws of physics are completely unrecognizable. The theory of the multiverse arose when physicists understood that quantum fluctuations need not be a one-time event. If the quantum vacuum had the power to generate our cosmos, it could surely generate others. In fact, the mathematics indicate that it must be producing them ceaselessly and without end, like bubbles forming on the surface of an infinite ocean. Each of these universes would start with its own Big Bang, expand through its own inflationary epoch, and evolve with its own distinct set of physical laws. Some might have stronger gravity, causing stars to live fast and die young. Others could have a weaker electromagnetic force, making the formation of atoms impossible. The vast majority would likely be barren wastelands, but a precious few might host forms of life beyond our wildest imagination. Imagine an eternal cosmic sea where every possible wave eventually takes shape. Our universe is merely one of these waves, transient and distinct, yet ultimately not special. The multiverse has no more concern for our existence than the ocean has for a single droplet of water. But here the concept becomes truly staggering. Certain versions of the multiverse theory propose an infinite number of universes, which means that every possible outcome of every event is realized somewhere. There exists a universe where the dinosaurs were never wiped out. There's a universe where gravity is a repulsive force. There's a universe where you chose a different path in life, becoming an artist instead of reading this. These parallel worlds are not just fanciful tales. They are a natural consequence of our most successful mathematical models of quantum mechanics and cosmic inflation. When you work through the equations that describe the quantum vacuum, the continuous creation of infinite universes emerges as an unavoidable result. The implications are both awe-inspiring and terrifying. If there are infinite universes, then every conceivable joy and every imaginable tragedy is playing out at this very moment. Every masterpiece that could be created already exists in some universe. Every scientific breakthrough that could be achieved has already been discovered in countless other realities. Some physicists take this idea even further, proposing that our multiverse might be just one tier in a far grander structure. There could be infinite multiverses, each containing infinite universes, stacked in layers of reality that stretch beyond human comprehension. But if these parallel universes exist, they may not remain parallel indefinitely. Quantum mechanics hints that universes might collide, merge, or interact in ways we are only just starting to conceive. The cosmic microwave background radiation, the faint afterglow of our own Big Bang, might bear the subtle scars of collisions with other universes that occurred billions of years ago. This prospect points toward an even more radical notion of what existed before our own beginning. What if our Big Bang was not the ultimate origin, but merely the latest reboot? Envision a cosmic phoenix, a universe that is consumed by fire every trillion years, only to be reborn from its own embers. Some physicists suggest our universe follows just such a pattern, cycling through endless iterations of expansion, collapse, and renewal. In this model, the Big Bang was not a creation out of nothing, but a transformation from a previous state. The cyclic universe model posits that our cosmos expands for billions of years, just as we see it doing now. But at some point, this expansion will slow, halt, and then reverse. Gravity will ultimately prevail, pulling every galaxy, star, and atom back together in a cataclysmic collapse known as the Big Crunch. But here is the critical twist. Rather than culminating in a final singularity, the Big Crunch triggers a new Big Bang. The universe rebounds from a state of maximum compression, erupting into a fresh cycle of expansion. Time does not cease during this transition. It flows through what physicists call a cosmic bounce. Picture it as a cosmic trampoline. Our universe is falling towards the trampoline's surface, gathering speed as it nears maximum density. Then, the inherent elasticity of reality kicks in, launching the universe back upwards into a new expansive phase. From the inside, each bounce would look just like a Big Bang, even though it is just one beat in an eternal cosmic rhythm. This model elegantly resolves several paradoxes that trouble the standard Big Bang theory. It provides an explanation for our universe's remarkable uniformity without needing the hyper-fast inflation that other models require. It also neatly sidesteps the question of what caused the Big Bang, as there was no singular beginning, only perpetual cycles. Recent findings of our universe's accelerating expansion, driven by the enigmatic force of dark energy, appear to contradict the idea of a future Big Crunch. However, proponents of the cyclic model have adjusted their theories to account for dark energy. They propose that the strength of dark energy might fluctuate over cosmic timescales, eventually shifting from a repulsive force to an attractive one, thereby initiating a contraction phase. In some of these cyclic cosmologies, each universal cycle lasts for approximately 1 trillion years. Our current cycle started 138 billion years ago, making our universe relatively young in the grand scheme. We would have hundreds of billions of years remaining before the expansion halts and the collapse commences. But each cycle might not be an exact replica of the last. Minor variations could build up over cosmic eons, making each new universe subtly different from the one that preceded it. Perhaps consciousness and complexity evolve to greater heights with each new cycle, as information is somehow preserved and carried over from one cosmic generation to the next. Other cyclic models imagine parallel universes taking turns expanding and contracting, like pistons in a colossal cosmic engine. While our universe is expanding, others are contracting. While some are exploding into new Big Bangs, we are cruising through our own phase of expansion. These concepts suggest that the question, what came before the Big Bang, has a straightforward answer: the previous universal cycle. But this only pushes the enigma one level deeper. What initiated the endless cycling in the first place? And could these cycles ever come to an end? Reality may possess 6 invisible dimensions, intricately wrapped around every single point in space. Right now, as you perceive this, you are immersed in dimensions that you cannot see, feel, or directly interact with. According to string theory, these hidden dimensions are curled up so tightly that they exist at every point in our familiar three-dimensional space, but on a scale so minuscule that even our most advanced instruments cannot resolve them. Imagine a long garden hose viewed from a great distance. It appears as a one-dimensional line, but as you move closer, you see it has a hidden circular dimension wrapped around its length. String theory posits that our universe functions in a similar way. What we perceive as three spatial dimensions plus one of time might actually be the unfolded aspects of a reality that contains 10 or even 11 dimensions in total. These extra dimensions are not empty. They are dynamic, shape-shifting arenas where the fundamental forces of nature conduct their business. The strengths of gravity, electromagnetism, and the nuclear forces in our familiar dimensions are determined by the geometry, the curvature and twisting of these hidden dimensions. In string theory, the ultimate constituents of reality are not point-like particles, but tiny, vibrating loops of energy called strings. These strings are unimaginably small, roughly 10 to the power of -35 meters in length. This is so diminutive that if you were to scale up a single atom to the size of our solar system, a string would still be smaller than a tree. The different vibrational patterns of these strings are what we perceive as different elementary particles. An electron is simply a string vibrating in one particular way. A photon is the same kind of string vibrating in a different pattern. A quark is yet another mode of vibration. It is like a cosmic orchestra where every distinct note corresponds to a different fundamental particle. But here is how this connects to our cosmic origins. String theory proposes that the Big Bang could have been sparked by a collision between higher dimensional objects known as brains. Our entire universe might be a three-dimensional membrane floating within a higher dimensional space, akin to a soap film on the surface of a multidimensional bubble. When two of these brains collide in this higher dimensional realm, the impact unleashes a tremendous amount of energy into each brain. From our perspective, living inside one of these brains, this release of energy would look exactly like a Big Bang. Time and space, as we experience them, would begin at the moment of this collision, but the brains themselves would have existed prior to the impact. This brain collision model offers explanations for several puzzles surrounding our universe's birth. It can account for the incredible smoothness of the cosmic microwave background radiation without resorting to faster-than-light inflation. It also implies that what we call the Big Bang was not a creation from absolute nothingness, but rather a transition from one state of the brain to another. The hidden dimensions might even harbor parallel brains, each hosting its own universe. These parallel realities could be less than a millimeter away from us in a higher dimension, yet remain completely inaccessible because we are confined to our own three-dimensional brain. This leads to an even more staggering possibility about the nature of cosmic creation. Somewhere in the cosmos, new universes are being born every single second. In the time you've been engaged with this narrative, countless Big Bangs have erupted in distant pockets of space, each giving rise to an entire cosmos filled with billions of galaxies. This is not a flight of fancy. It is the logical outcome of eternal inflation theory, one of the most compelling models in modern cosmology. Standard inflation theory describes how our universe swelled from a subatomic scale to a cosmic one in its first moment of existence. But eternal inflation proposes that this process, in fact, never truly ceases. It simply shifts from one region to another, generating an unending sequence of pocket universes within an ever-expanding multiverse. Picture a vast pot of boiling water where bubbles constantly form and detach from a surface. Each of these bubbles represents a universe like ours, complete with its own space, time, and physical laws. The boiling water symbolizes the inflating field that permeates the multiverse, forever birthing new bubbles of reality. Our observable universe is merely the interior of one such bubble. The Big Bang was not the beginning of everything, but the moment when our local patch of space ceased its rapid inflation and settled into the more leisurely expansion we see today. But beyond our bubble, the cosmic inflationary field continues its exponential growth, periodically spawning new pocket universes. This process has no start and no end. Even if inflation began at some point in the far past, once it starts, it generates an infinite amount of future time and an infinite amount of space. The multiverse expands so rapidly that regardless of how many pocket universes are formed, there is always room for infinitely more. Each pocket universe could possess different physical constants. In some, gravity might be stronger, causing stars to burn out in a flash. In others, the electromagnetic force could be weaker, preventing the formation of complex chemistry. The majority of these pocket universes would be sterile, but on rare occasions, one would have the precise conditions necessary for complexity and life to arise. The distances separating these pocket universes are unimaginably vast. They are divided by regions of space that are still inflating, expanding faster than light can traverse them. Even if you could travel at the speed of light for an eternity, you would never reach another pocket universe because the space between you and it is growing faster than you can cross it. But here is the truly mind-altering part. In an eternally inflating multiverse, every possible universe must exist somewhere. There is a pocket universe where the laws of physics permit travel faster than light. There is another where time flows in reverse. There is even one where the physical constants are so exquisitely tuned that black holes can naturally evolve into conscious entities. This infinite production of realities raises profound questions about the very nature of existence. If every possible universe is real, then the distinction between possibility and actuality dissolves. Everything that can happen does happen somewhere in the eternal multiverse. Some physicists are concerned that eternal inflation undermines science by predicting that anything is possible. Others embrace it as the most elegant solution to why our own universe appears so perfectly calibrated for complexity and life. But even eternal inflation leaves a deeper enigma unresolved. At the very edge of the Big Bang, our mathematics themselves fall apart. Physicists have successfully traced the history of our universe back to a minuscule fraction of a second after its inception. They can describe the formation of the first atomic nuclei, the birth of the first stars, and even the instant when space became transparent to light. But there is one threshold they cannot cross, a single moment where all of their equations devolve into nonsense. This boundary is known as the Planck epoch, a period lasting from time 0 to approximately 10 to the power of negative 43 seconds after the Big Bang. During this incomprehensibly brief interval, the universe was so intensely hot and dense that quantum effects governed gravity itself. Space and time became granular and uncertain, like a photograph magnified until its individual pixels are visible. At this Planck scale, the smooth tapestry of space-time, described by Einstein, is torn into a quantum foam. Distances smaller than the Planck length, about 10 to the power of negative 35 meters, lose their meaning. Time intervals shorter than the Planck time, roughly 10 to the power of negative 43 seconds, cannot be measured, even in principle. Imagine trying to use a ruler composed of atoms to measure something smaller than an atom. The ruler itself becomes the limitation. In the same way, when we attempt to probe the Planck epoch, our very concepts of space and time are the limiting factor. We're trying to use space-time to comprehend the origin of space-time. This leads to what physicists refer to as the boundary problem. Every equation in physics operates on the assumption that space and time exist as a background arena for events to occur. But at the moment of the Big Bang, there was no such arena. The stage itself was being created, along with the very concepts of moment and creation. Einstein's theory of general relativity, our premier theory of gravity and space-time, predicts that all matter was compressed into a mathematical point of infinite density known as a singularity. However, infinities in physics are typically a red flag, indicating that a theory has been pushed beyond its limits of applicability. Reality does not actually contain infinities. Our mathematical tools simply fail. Quantum mechanics suggests that this singularity should be replaced by something else, perhaps a region of maximum possible density where space and time are quantized, much like the energy levels of an atom. But we currently lack a complete theory of quantum gravity to describe this realm. Some physicists propose that asking what occurred before the Planck epoch is analogous to asking what lies north of the North Pole. Time itself might have a boundary, a first moment that was not preceded by any other moment. In this view, the Big Bang represents the absolute genesis of temporal existence. Others suggest that time might be an emergent property, arising from more fundamental, timeless processes. Just as temperature emerges from the collective motion of countless atoms, time might emerge from quantum interactions in a deeper reality that does not experience duration. This boundary problem directs us toward one of the most profound mysteries in all of science: the relationship between information and existence itself. Before the universe came into being, where was the information required to construct it? Every particle in your body, every atom in every star, every quantum state in every galaxy embodies information. Your DNA contains the informational blueprint for your biological form. The quantum states of electrons in your brain store the information of your thoughts and memories. The universe is, at its core, composed of information. But what was the original source of all this information? Consider a simple hydrogen atom, the most basic element in the cosmos. Even this seemingly simple system holds precise information about its electrons' energy level, spin, and orbital shape. Now multiply this by every atom in every galaxy, and the quantity of information in our observable universe becomes astronomically vast. Traditional physics views information as something that is encoded onto pre-existing matter and energy. But quantum mechanics uncovers something strange. Information itself may be more fundamental than the matter and energy that convey it. In quantum systems, the information defining a particle's state determines what the particle is rather than the other way around. This leads to a paradox that strikes at the heart of cosmic origins. If our universe emerged from quantum fluctuations in a vacuum, where did the informational content of those fluctuations originate? Empty space should not contain the immense libraries of data needed to specify the properties of billions of galaxies. Some physicists propose that information is conserved, just like energy, meaning it can neither be created nor destroyed, only transformed. According to this view, the information content of our universe must have existed in some form before the Big Bang. But this simply pushes the mystery to another level. What was the storage medium for all that information before space and time came into being? The holographic principle provides a mind-bending solution. It suggests that all the information contained within a three-dimensional volume of space can be encoded on the two-dimensional boundary of that region, much like a hologram stores a complete three-dimensional image on a flat surface. When applied to cosmology, this implies that all the information in our universe might be encoded on its boundary at the cosmic horizon. From this perspective, our three-dimensional reality could be a projection of information stored on a distant two-dimensional surface. We could be living inside a cosmic hologram without ever knowing it. But this still does not explain where the boundary information came from in the first place. Some theorists propose that information is truly fundamental, existing independently of space, time, matter, and energy. In this view, physical reality emerges from pure information processing, like a cosmic computer running the program we call the universe. If information is fundamental, then asking where it came from might be like asking why mathematics is effective. The information simply is a basic feature of reality that requires no further explanation. Our universe would be one possible configuration of this primordial information, selected by processes we have yet to comprehend. This first glimpse of reality points toward an even stranger possibility about the nature of existence itself. True nothingness might be logically impossible. Picture perfect emptiness. No matter, no energy, no space, no time, no fields, no forces, and no potential for anything to ever occur. This is what most people conceive of as absolute nothingness. But quantum mechanics suggests that such a state cannot exist, even in principle. The reason is rooted in the uncertainty principle, one of the foundational laws governing reality at its most minute scales. This principle dictates that you can never simultaneously know both the precise position and the precise momentum of any particle. But its application extends beyond particles. It also applies to energy and time, and to the quantum fields that permeate all of space. In a region of perfect emptiness with exactly zero energy, you would know the energy with absolute certainty. But the uncertainty principle forbids such perfect knowledge. Therefore, the energy must fluctuate, borrowing from and repaying the quantum vacuum in a cosmic game that never ceases. These fluctuations are not mere mathematical quirks. They have real, observable consequences. Virtual particles pop into existence, exist for a fleeting moment, and then annihilate each other and vanish. The more energetic the fluctuation, the shorter its duration. But during that brief instant, borrowed energy can give rise to temporary realities. Now, here is the truly astonishing part. If quantum fluctuations can occur in empty space, they should also be able to occur in the absence of space itself. Pure nothingness, if it could exist, would still be governed by quantum uncertainty. This implies that nothingness would fluctuate, creating something from nothing through the fundamental laws of quantum mechanics. These fluctuations in pure nothingness would not be restricted to tiny particle pairs. The uncertainty principle permits enormous fluctuations, provided they last for incredibly short periods. A fluctuation large enough to create an entire universe would be allowed, as long as it repays its borrowed energy quickly enough. But this is where cosmic inflation enters the scene. If this universal fluctuation inflated rapidly enough, it could expand to a size larger than its own quantum wavelength before the time for repayment expired. Once this occurs, the fluctuation becomes real and permanent, transitioning from a state of borrowed existence to one of actual existence. Think of it as a quantum credit card with an infinite spending limit but an immediate repayment demand. Most transactions are reversed almost instantly, but occasionally, a purchase grows so immense that it escapes the system's ability to reclaim it. The debt becomes real, but so does the purchase. Our entire universe might be the outcome of such a quantum fluctuation that grew too large to be reversed. From this viewpoint, existence itself is a kind of cosmic accident, a quantum hiccup that inflated beyond the point of no return. But if one universe can fluctuate into being from pure nothingness, then others should be fluctuating into existence all the time. Pure nothingness, if it ever existed, would be inherently unstable, perpetually spawning endless realities through quantum uncertainty. This raises a profound question. If nothingness is impossible, has something always existed? The answer leads us to contemplate the role of consciousness itself. What if the universe requires observers in order to exist? Quantum mechanics confronts us with a puzzle that has troubled physicists for nearly a century. Before being measured, particles exist in a superposition of multiple states at once, spread out in a cloud of possibilities. But the instant they are observed, these possibilities collapse into a single, definite reality. The very act of observation appears to create the reality being observed. This is not a philosophical proposition. It is experimentally verified science. Electrons can be in multiple locations simultaneously until they are detected. Photons can travel along multiple paths at once until they are measured. The quantum world remains fundamentally indefinite until consciousness interacts with it. But here is the mind-bending question. If observation brings reality into being, what observed the universe before conscious beings evolved? How could the cosmos have existed for billions of years before the first minds appeared to collapse its quantum possibilities into definite states? Some physicists have proposed that consciousness itself might be a fundamental aspect of the cosmos, not something that emerged from complex arrangements of matter, but something that was present from the very beginning. In this view, the Big Bang was not just the creation of matter and energy, but the first moment when a cosmic consciousness began to observe itself. Imagine reality as a vast quantum computation, with consciousness as the processor that transforms possibilities into actualities. Without consciousness to run the program, the universe would remain a cloud of unrealized potential, forever suspended in a state of quantum superposition. This idea suggests that what existed before the Big Bang was pure consciousness without any content, an infinite potential awareness with nothing yet to be aware of. The Big Bang would then represent the moment when this consciousness began to observe itself, creating space, time, and matter through the act of self-observation. But if consciousness creates reality through observation, then different types of consciousness might create different types of reality. Human consciousness, with its specific patterns of attention and measurement, could be shaping the universe in ways that reflect our own cognitive structures. An alien consciousness, with different sensory systems and mental frameworks, might observe a fundamentally different universe into existence. This raises extraordinary possibilities about parallel realities. Every conscious decision you make could potentially split the universe, creating branches where different choices are realized. Every observation you make might be selecting one reality from a countless number of quantum possibilities. Your consciousness might not just be observing the universe. It could be participating in its creation moment by moment. Some interpretations of quantum mechanics suggest that all possible realities exist simultaneously in a vast multiverse. But consciousness selects which branch of this multiverse it experiences. From this perspective, before the Big Bang, all possible universes existed as pure potential. The emergence of consciousness created the first definite reality by selecting one possibility from an infinite quantum menu. If consciousness is fundamental rather than emergent, then it might be the one thing that does not need to be created or explained. It simply is like existence itself. The universe might be consciousness exploring its own infinite potential through the experience of space, time, and matter. This leads us to an even more radical possibility concerning the relationship between mind and mathematics. What if reality is literally constructed from mathematics? Right now, you might believe you're reading words made of matter, sitting on a physical chair, and breathing real air. But according to the mathematical universe hypothesis, you're actually experiencing mathematical structures so complex that they have become self-aware. You are not composed of atoms and molecules. You are composed of numbers and equations that have learned how to think. This is not intended as a metaphor or an analogy. The MIT physicist Max Tegmark has seriously proposed that mathematical existence and physical existence are one and the same. Every electron, every photon, and every quantum field is, in fact, a mathematical object. The universe does not simply adhere to mathematical laws, it is mathematics. Consider what mathematics truly represents. When you use algebra to describe the motion of an object, you're not creating an approximation of reality. You're uncovering the actual structure of reality itself. The equations do not describe something else, they are the something else. Physical objects are mathematical objects that have attained sufficient complexity to interact with themselves. This idea resolves a puzzle that has perplexed scientists for centuries. Why is mathematics so unreasonably effective at describing the natural world? The answer is simple. Mathematics works perfectly because reality is mathematics. We are not discovering mathematical approximations of physical laws. We are discovering the very mathematical structures that constitute existence. But here is where it becomes truly mind-bending. If our universe is a mathematical structure, then every possible mathematical structure should also exist as a physical universe. There is a universe based on different geometries, where space has 4 dimensions instead of 3. There is a universe where the mathematical constants have different values, causing physics to operate differently. Every mathematical theorem, every possible equation, and every conceivable logical system corresponds to an actual universe somewhere in the grand ensemble of all mathematical reality. Our universe happens to be described by the particular mathematics we observe, but countless other universes are described by different mathematics. From this perspective, the Big Bang was not the creation of matter and energy from nothing. It was the moment when a particular mathematical structure became complex enough to support observer moments, conscious experiences embedded within a mathematical framework. You are not a biological creature observing a mathematical universe. You are a mathematical pattern that has achieved self-awareness. This explains what existed before the Big Bang. Mathematics itself existed in all its infinite complexity and possibility. The ensemble of all mathematical structures was complete and eternal, containing every possible universe as a subset. Our Big Bang represents the moment when observers first appeared within one particular mathematical structure. Time itself becomes an illusion in this view. The mathematical structures that constitute reality exist timelessly, like geometric theorems. We experience the passage of time because we are embedded within structures that contain temporal sequences. But from a perspective outside the structure, all moments exist simultaneously. The mathematical universe hypothesis suggests that consciousness is not something separate from mathematics, but rather what complex mathematics feels like from the inside. When mathematical structures become sufficiently intricate and self-referential, they generate subjective experience. This leads us to confront one of the deepest mysteries in all of cosmology. Dark energy should not exist, yet it is tearing our universe apart. In 1998, astronomers made a discovery that shattered everything physicists thought they knew about the destiny of the cosmos. Instead of slowing down under the influence of gravity, the expansion of the universe was accelerating. Something was pushing galaxies apart with ever-increasing force, and nobody had any idea what it was. They named this mysterious force dark energy, and it constitutes about 70% of everything that exists. Dark energy is invisible, detectable only through its effects on cosmic expansion, and it completely defies our understanding of how energy should behave. Normal energy becomes diluted as space expands, like perfume diffusing through a room. Dark energy, however, becomes more dominant. The leading explanation involves the cosmological constant, a term Einstein added to his equations to create a static universe. He later referred to it as his greatest blunder when observations revealed that the universe was, in fact, expanding. But the recent discovery of accelerating expansion suggests that Einstein's blunder was actually a profound insight into the nature of reality. The cosmological constant represents the energy density of empty space itself. Even a perfect vacuum contains energy, and this vacuum energy creates a repulsive force that pushes space apart. It is as if the universe is filled with an invisible substance that causes space itself to want to expand. But here's the problem that keeps physicists awake at night. When you calculate the amount of vacuum energy that empty space should contain using quantum mechanics, you get a number that is 10 to the 120th power larger than what we observe. This is not a minor discrepancy. It is the single worst prediction in the history of science. If quantum mechanics is correct about vacuum energy, our universe should be expanding so rapidly that atoms could not form, stars could not shine, and galaxies could not exist. The very fact that we are here to ask these questions means that somehow the universe has tuned its vacuum energy to a value incredibly close to zero, but not exactly zero. This fine-tuning is so precise that it seems impossible to have occur by chance. It is like balancing a pencil on its sharpest point for billions of years while the table is being shaken by earthquakes. Yet somehow, the universe has achieved this impossible equilibrium. Some physicists propose that what we call dark energy is not vacuum energy at all, but some other field that mimics the effects of the cosmological constant. Others suggest that the laws of physics themselves might evolve over cosmic time, with the cosmological constant changing as the universe ages. The multiverse offers another explanation. If infinite universes exist, each with a different value for vacuum energy, most would either expand too quickly or collapse too rapidly for complexity to develop. We observe a universe with the right cosmological constant because we could not exist in a universe with the wrong value. But this raises an even deeper mystery. Why do the fundamental constants of nature appear to be so perfectly tailored for the existence of complexity, consciousness, and life? The answer might reveal the deepest secret about what came before our cosmic beginning. The force that is destroying our universe might be a remnant from its creation. Dark energy remains the greatest enigma in modern physics, but its origin story could be written in the very first moments after the Big Bang. Some physicists propose that dark energy is actually fossil energy from cosmic inflation, the period of rapid expansion that stretched our universe from subatomic size to a cosmic one in its first fraction of a second. During inflation, space itself expanded faster than light, driven by a quantum field called the inflaton. This field possessed an enormous energy density, enough to create all the matter and energy we see today when inflation finally concluded. But what if inflation never entirely ceased? What if a minuscule remnant of the inflaton field still permeates all of space? This remnant would not be powerful enough to drive the rapid inflation of the early universe, but it could provide the gentle push that is accelerating cosmic expansion today. Dark energy might be the dying breath of the force that created our universe, still echoing through space after nearly 14 billion years. Think of it like the ripples from a stone cast into a perfectly still pond. Long after the stone has sunk and the initial splash has dissipated, tiny ripples continue to spread outward. Dark energy could be the final ripple from the cosmic inflation that birthed our universe. But here is where it gets even stranger. If dark energy originates from leftover inflation energy, then its density should slowly decrease as the universe expands. Eventually, it should fade away completely, allowing gravity to once again slow down cosmic expansion. Our current phase of acceleration would be a temporary phenomenon, a transitional period between a matter-dominated past and an unknown future. Other theories suggest that dark energy might be increasing in strength rather than decreasing. If this is true, cosmic expansion will accelerate faster and faster until it tears apart galaxies, solar systems, atoms, and eventually space itself. This scenario, known as the Big Rip, would bring our universe to an end in about 22 billion years, when the expansion becomes so violent that the very fabric of space-time is shredded. Alternatively, dark energy might oscillate, sometimes driving expansion and at other times resisting it. This could lead to cycles of acceleration and deceleration, perhaps even resulting in future periods of cosmic contraction and new Big Bang events. The most unsettling possibility is that dark energy represents a fundamental instability in the quantum vacuum itself. Our current vacuum state might be a false vacuum, temporarily stable, but destined to decay into a lower energy state. When this happens, a bubble of true vacuum will expand at the speed of light, destroying everything in its path and rewriting the laws of physics. This vacuum decay could have already started somewhere in the observable universe. The bubble of destruction would be invisible until it arrives, traveling at the speed of an unerring light speed and erasing reality as it expands. We would have no warning. Dark energy forces us to confront the possibility that our universe's apparent stability is an illusion, a temporary calm before an inevitable storm that will reshape or annihilate everything we know. The universe appears to be designed for our existence, and no one knows why. Right now, you exist because of the most incredible cosmic coincidence in all of science. The forces that govern reality are balanced with such exquisite precision that altering any one of them by even a minuscule amount would make stars impossible, atoms unstable, or any form of complexity utterly forbidden. Consider gravity, the weakest of the fundamental forces. If gravity were just slightly stronger, stars would burn through their fuel in millions of years instead of billions, never allowing enough time for life to evolve. If gravity were slightly weaker, stars would never form in the first place, as gas clouds would be unable to collapse under their own weight. The electromagnetic force demonstrates the same impossible precision. If it were a little stronger, electrons would be bound so tightly to atomic nuclei that chemistry would be impossible. If it were weaker, atoms would fall apart, making molecules and complex structures prohibited by the laws of physics. The strong nuclear force, which holds atomic nuclei together, is tuned even more finely. If you were to change it by just 5% in either direction, you would eliminate either carbon or oxygen from the universe. Without both of these elements, the chemistry of life, as we know it, would be impossible. But the most shocking example involves the cosmological constant that drives dark energy. As we have discussed, quantum mechanics predicts that this constant should be 10 to the power of 120 times larger than what is observed. Yet somehow, it is tuned to be almost exactly zero, allowing the universe to exist for billions of years instead of expanding so rapidly that matter could never clump together. The probability of all these constants randomly falling within the narrow ranges that permit complexity is essentially zero. It is like throwing a dart from a million miles away and hitting a target the size of a single atom. The odds are so infinitesimally small that it might as well be impossible. This fine-tuning problem compels us to ask uncomfortable questions about the nature of reality. Did some entity or process deliberately set these constants? Are we living in a designed universe, specifically crafted to allow for the emergence of consciousness and complexity? Most physicists reject the notion of intelligent design, but they are left with equally mind-bending alternatives. The multiverse hypothesis suggests that an infinite number of universes exist, each with random physical constants. Most of these universes are sterile wastelands, but we observe a fine-tuned universe simply because we could not exist in any other kind. The Anthropic principle extends this idea, suggesting that the universe must be compatible with consciousness because conscious observers are here to study it. We do not observe random physical constants because random constants typically do not produce observers. But some physicists propose that consciousness itself might play a role in selecting the physical constants through quantum measurement effects. If observer moments help to collapse quantum possibilities into definite realities, then the very act of observation might be literally tuning the universe to be compatible with observers. This leads to the most radical possibility of all, that consciousness and physical reality co-evolve, each shaping the other in ways we are only just beginning to comprehend. Other universes might be colliding with ours at this very moment. As you read these words, our universe could be interacting with parallel realities in slow motion, leaving subtle fingerprints across the cosmic sky. These collisions would not be destructive events that annihilate galaxies or planets. They would occur so gently that only our most sensitive instruments could ever hope to detect their traces. According to eternal inflation theory, our universe is just one bubble in an infinite foam of realities. Most of these bubble universes are expanding away from each other faster than the speed of light, making any form of contact impossible. But occasionally, two bubbles might form close enough together that their boundaries could touch before cosmic expansion pulls them apart. When the boundaries of these universes collide, they do not crash and explode like vehicles in an accident. Instead, they would interact through the quantum fields that exist on both sides of the collision zone. These field interactions would release energy that would propagate through both universes in the form of gravitational waves and radiation. From within our universe, such a collision would appear as a circular pattern in the cosmic microwave background radiation. the ancient light that fills the sky from the afterglow of the Big Bang. The collision zone would create a subtle warm or cool spot in this radiation, like a cosmic bruise marking the point where another reality touched ours. Several research teams have claimed to have found such patterns in the data from the cosmic microwave background, although other scientists remain skeptical of these findings. The signatures are so faint that they are difficult to distinguish from random fluctuations or instrumental noise. It is possible that we already have evidence of parallel universe collisions, but we cannot yet be certain. If collisions between parallel universes are real, they could happen multiple times as our cosmic bubble encounters different neighbors during its expansion. Our sky might contain several such collision signatures from different parallel realities, each one marking a brief moment of contact with an alternative cosmos. But here is the truly mind-bending possibility. If universe collisions can occur, they might also allow for the exchange of information across the boundary. Quantum fields could potentially carry data from one universe to another during the collision process, creating a form of interdimensional communication. Some physicists speculate that consciousness itself might be able to tunnel between colliding universes under special circumstances. If awareness is a quantum phenomenon, as some theories suggest, then parallel universe collisions might briefly connect the conscious experiences in different realities. This could offer an explanation for certain strange phenomena, such as the feeling of having memories of events that never happened or sensations of déjà vu that seem to come from nowhere. Perhaps your consciousness occasionally receives echoes from parallel versions of yourself, living in nearby universes that briefly touch our own reality. The implications of this extend beyond individual experience. Entire civilizations in parallel universes might be attempting to send messages across dimensional boundaries during these collision events. The cosmic microwave background could contain encoded information from advanced beings trying to communicate across the multiverse. Future technologies might one day allow us to decode these interdimensional messages and even send replies of our own, establishing contact with parallel versions of Earth and humanity. We might discover that consciousness has a natural inclination to seek connection across all possible realities. Your entire reality might be a projection from a distant boundary. Right now, as you experience the three-dimensional world around you, you might actually be observing a hologram projected from information stored on a two-dimensional surface billions of light years away. This is not mere science fiction speculation. It is a serious theory supported by cutting-edge physics and observational evidence. The holographic principle emerged from studies of black holes, where physicists discovered something that seemed impossible. When matter falls into a black hole, it appears to vanish from our universe forever. But quantum mechanics dictates that information can never be destroyed, creating a paradox that threatened to undermine the fundamental laws of physics. The solution came from the realization that information falling into a black hole is not actually destroyed. It is encoded on the black hole's two-dimensional surface, the event horizon. From our perspective outside the black hole, the information never quite crosses the event horizon. Instead, it spreads out across the surface, creating a complete record of everything that has ever fallen in. This discovery led physicists to a startling conclusion. If all the information contained within a black hole's three-dimensional interior can be encoded on its two-dimensional surface, then perhaps all the information in any three-dimensional region can be encoded on its boundary. When applied to cosmology, this means our entire observable universe, with all its galaxies, stars, planets, and life forms, might be information encoded on a distant two-dimensional boundary. We experience three dimensions because that is how the information is processed and projected, but the fundamental reality exists on a cosmic horizon that we can never reach. Think of watching a movie on a screen. The movie appears to be three-dimensional and full of complex action, but it is actually just patterns of information on a flat surface. The holographic principle suggests that our universe works in a similar way, with all of reality's complexity emerging from information patterns on a distant boundary. This idea explains several puzzles about quantum mechanics and gravity. It suggests that what we call space might be an emergent phenomenon arising from quantum entanglement between different regions of the boundary information. The distance in our three-dimensional world would correspond to the degree of entanglement between these boundary regions. The holographic principle also offers insights into what existed before the Big Bang. If our universe is a holographic projection, then the Big Bang would represent the moment when information processing began on the cosmic boundary. Before this moment, the boundary would have existed in some dormant state, containing the potential for our reality but not yet projecting it. Some versions of the holographic principle suggest that consciousness itself might be the projection mechanism, transforming boundary information into experienced reality through the act of observation. In this view, conscious beings are not separate from the holographic projection. They are part of the processing system that creates the projection. This leads to an extraordinary possibility. If reality is holographic, then the apparent separation between different conscious beings might be an illusion. All observers could be different aspects of a single information processing system, experiencing itself from multiple perspectives simultaneously. The boundary between self and universe dissolves in the holographic paradigm. Time might not exist at the most fundamental level of reality. Right now, you feel time flowing from the past to the future, carrying you forward through a sequence of moments that seem to unfold in order. But this experience might be a convincing illusion, created by the complex arrangement of matter and energy in your brain. At the deepest level of reality, time may not exist at all. Think of a movie recorded on film. The individual frames all exist simultaneously in reality, but when they're played in sequence, they create the illusion of motion and temporal flow. Similarly, all the moments in the history of our universe might exist simultaneously in a timeless realm, with consciousness creating the illusion of temporal flow by experiencing these moments in a particular sequence. This idea emerges from studying the fundamental equations of physics. Einstein's theory of general relativity treats time as just another dimension, no different from the three dimensions of space. The past, the present, and the future all exist equally in what physicists call the block universe. Your birth, your death, and every moment in between exists simultaneously in this four-dimensional space-time block. Quantum mechanics suggests something even more radical. At the quantum level, events do not happen in a definite sequence until they are observed. Particles can exist in superpositions of past and future states simultaneously. The quantum universe exists in a timeless realm of pure possibility until consciousness collapses these possibilities into experience sequences. Some physicists propose that time emerges from quantum entanglement between different parts of the universe. As quantum systems become entangled with one another, they create correlations that give rise to the arrow of time. The past is the direction of less entanglement. The future is the direction of more entanglement, and the present is the evolving boundary between them. This emergence of time from a timeless foundation might explain what existed before the Big Bang. In a timeless realm, there is no before because there is no temporal sequence. All possible moments, including those we might label as before the Big Bang, exist simultaneously in a timeless ensemble. The Big Bang would not represent the beginning of time, but rather the beginning of temporal experience. It would mark the moment when quantum entanglement became complex enough to create the subjective experience of temporal flow. Before this threshold, reality existed in a timeless quantum superposition of all possibilities. Consciousness plays a crucial role in this picture. The experience of time might be what information processing feels like from the inside. Your brain creates a temporal experience by integrating information from past states and predicting future states. Time is not something you move through. It is something your consciousness creates through the act of information integration. This suggests that different types of consciousness might experience time differently. An artificial intelligence with different information processing patterns might experience temporal flow in ways that are completely alien to human perception. Advanced alien civilizations might have learned to manipulate their temporal experience, speeding up or slowing down their subjective perception of time. If time is emergent rather than fundamental, then the question of what came before the Big Bang becomes meaningless in a deeper sense. Why does the universe seem to be custom-built for observers like us? The Anthropic principle begins with a simple observation that leads to mind-bending conclusions. We exist, therefore the universe must be compatible with our existence. This might sound trivially obvious, but it is actually one of the most profound and controversial ideas in modern cosmology. The weak Anthropic principle simply states that we observe a universe that is compatible with conscious observers because we could not observe any other type. In universes where stars cannot form, chemistry does not work, or complexity is impossible, there would be no conscious beings to notice the inhospitable conditions. We necessarily find ourselves in a universe that allows for the emergence of consciousness. But the strong Anthropic principle goes much further. It suggests that the universe must have properties that make the emergence of consciousness inevitable, not just possible. In this view, the fundamental constants of nature are not randomly chosen, but are somehow required to have values that ensure conscious observers will eventually appear. This leads to uncomfortable questions about the relationship between mind and cosmos. Did the universe somehow know that conscious beings would emerge billions of years later when it set its physical constants during the first moments after the Big Bang? Or do conscious observers play an active role in determining the constants through some kind of retrocausal quantum effect? Some interpretations of quantum mechanics suggest that conscious observation does not just reveal pre-existing realities, but actually selects which reality exists from a multitude of quantum possibilities. If this is true, then the mere fact that conscious observers exist in our universe might explain why the physical constants are so finely tuned for consciousness. Think of it as a cosmic selection effect that operates across time. All possible universes with different physical constants exist in a state of quantum superposition until conscious observers appear. The act of observation then retroactively selects the branch of a universe where consciousness is possible, explaining why we find ourselves in such a fine-tuned reality. The participatory Anthropic principle pushes this idea to its logical limit. It suggests that conscious observers do not just select which universe they observe, but actively participate in creating the universe through their observations. Reality becomes a collaboration between quantum possibilities and conscious choice, with neither existing independently of the other. Critics argue that anthropic reasoning is unscientific because it cannot make testable predictions. If we can only observe universes that are compatible with observers, then we can never test whether other types of universes exist. The Anthropic principle becomes an untestable philosophical position rather than a scientific hypothesis. Supporters counter that anthropic reasoning does make specific predictions about what we should observe in a multiverse scenario. It predicts that physical constants should be close to the boundary values that allow for complexity, which is consistent with our observations. It also predicts that we should find ourselves in a typical location within the set of observer-compatible universes. The anthropic debate forces us to confront the deepest questions about existence itself. Are conscious observers accidental byproducts of cosmic evolution, or are they somehow fundamental to the nature of reality? The answer might determine whether consciousness is rare in the cosmos or inevitable. Our universe might be living on borrowed time. Right now, the quantum vacuum that surrounds you appears to be stable and unchanging. But it might actually be a false vacuum, a state that is temporarily stable but is destined to decay into a lower energy state. When this happens, a bubble of true vacuum will expand at the speed of light, destroying everything in its path and rewriting the laws of physics themselves. Think of a ball balanced on top of a hill. It looks stable, but it is actually in a state of false equilibrium. The slightest disturbance will send it rolling down to the true minimum at the bottom of the hill. Our vacuum might be like that ball, precariously balanced in a state that seems stable but is not truly stable. This idea emerges from studying the Higgs field, the quantum field that gives particles their mass. Current measurements suggest that the Higgs field might exist in a metastable state, which means that it is stable for now, but could spontaneously decay into a lower energy configuration. This decay would catastrophically alter the properties of matter throughout the universe. When vacuum decay begins, it creates an expanding bubble where the laws of physics work differently. Inside this bubble, particles might have different masses, forces might have different strengths, and atoms might not be able to form at all. The wall of this bubble moves at exactly the speed of light, so there would be no warning of its approach. From our perspective, vacuum decay would be the ultimate cosmic catastrophe. We would not be able to see it coming because the destruction travels at the speed of light, the fastest possible speed for information transfer. One moment, we would be living our normal lives. The next, we would be erased as the bubble wall passed through our location. But here is the truly disturbing part. Vacuum decay might have already begun somewhere in the observable universe. A decay bubble could be expanding toward us right now from a distant galaxy, and we would have no way to detect it until it arrives. The universe might already be doomed, with destruction racing toward us at 186,000 miles per second. The probability of spontaneous vacuum decay is extraordinarily low under normal conditions. The vacuum might remain stable for periods longer than the current age of the universe. However, certain events could trigger the decay process, such as high-energy particle collisions or the extreme gravitational fields near black holes. Some physicists have expressed concern that particle accelerators might accidentally trigger vacuum decay by creating conditions that push the Higgs field over the edge into its true ground state. Others argue that cosmic ray collisions already produce energies far higher than any human-made accelerator. So if vacuum decay were easily triggered, it would have happened naturally long ago. If vacuum decay is a possibility, it raises profound questions about the ultimate fate of consciousness and information in our universe. Would advanced civilizations find ways to survive the transition to the true vacuum? Perhaps by encoding themselves in forms of matter that would remain stable under the new physics. The possibility of vacuum decay connects to deeper questions about what lies beyond our current understanding. The mystery of our cosmic beginning points toward an even stranger ending. Every theory about what existed before the Big Bang carries with it implications for where our universe is heading. If we emerge from a process of eternal inflation, we might eventually return to it. If we are part of a cyclic cosmos, we might be destined to collapse and rebound. If we are living in a false vacuum, we might face annihilation through vacuum decay. The far future of our universe depends on the behavior of dark energy, the mysterious force that is accelerating cosmic expansion. Current observations suggest three possible destinies, each more alien than the last. If dark energy remains constant, we face the heat death scenario, where the expansion continues forever until all the stars have burned out and all the black holes have evaporated, leaving a cold, empty cosmos filled only with elementary particles drifting through an infinite void. If dark energy increases over time, we face the Big Rip, where the acceleration becomes so violent that it tears apart galaxies, solar systems, atoms, and finally space-time itself. The universe would end about 22 billion years from now, when the expansion becomes infinite and the very fabric of reality is shredded. If dark energy decreases or reverses its effect, we might face the Big Crunch, where cosmic expansion slows, stops, and reverses. All matter would collapse back toward a single point, potentially triggering a new Big Bang and beginning the cycle anew. But these classical scenarios might be missing something profound about the relationship between consciousness and the cosmos. If consciousness plays a fundamental role in quantum mechanics, as some interpretations suggest, then the far future might depend on whether conscious observers survive to collapse quantum possibilities into definite realities. Advanced civilizations billions of years in the future might face a choice that determines the ultimate fate of existence itself. They could allow consciousness to fade away as the stars die and energy becomes scarce, leading to a universe of pure quantum possibility with no observers to actualize any particular reality. Alternatively, they might find ways to preserve consciousness indefinitely, perhaps by encoding minds in forms that can survive cosmic expansion, heat death, or even vacuum decay. These future minds might discover technologies for manipulating the quantum vacuum, creating new universes, or escaping to higher dimensions. The strangest possibility involves consciousness actively shaping the universe's destiny through quantum measurement effects. If observation helps to determine reality, then the conscious choices made by future civilizations might retroactively influence the physical constants that determined whether consciousness could emerge in the first place. This creates a kind of temporal loop where the ultimate fate of consciousness determines the initial conditions that allowed consciousness to exist. The universe might be structured as a self-consistent causal loop, with its beginning and ending connected through quantum mechanical relationships that transcend ordinary time. If this is true, then asking what came before the Big Bang becomes equivalent to asking what consciousness will choose to become in the far future. The mystery of cosmic origins might only be solved by conscious beings who survive to the end of time and discover their role in creating the beginning. This brings us to one of the deepest questions in all of existence. Everything that ever happens might be recorded forever in the fabric of reality. Right now, as you read these words, information about this moment is being encoded into the quantum structure of space-time itself. Every thought in your mind, every photon striking your eyes, and every quantum interaction in your body creates permanent records that might persist long after the stars have died and the galaxies have faded. The principle of information conservation states that information can never be truly destroyed, only transformed from one form to another. This is not just a mathematical convenience. It appears to be a fundamental law of nature, as real as the conservation of energy or the speed of light limit. When you burn a book, the information contained in its pages does not vanish. It gets encoded in the precise positions and velocities of smoke particles, ash fragments, and electromagnetic radiation. In principle, if you could track every particle and photon produced by the fire, you could reconstruct the original text perfectly. The same principle applies to black holes, those cosmic monsters that seem to devour everything that falls into them. Stephen Hawking initially thought that black holes destroyed information permanently, creating a paradox that threatened to break the laws of physics. But subsequent research suggests that the information that falls into black holes gets encoded on their surfaces and is slowly released through Hawking radiation as the black holes evaporate. This leads to a staggering conclusion about cosmic history. Every event that has ever occurred in our universe, from the first quantum fluctuations after the Big Bang to the last thoughts of dying civilizations, might be preserved forever in the quantum information structure of reality. Think of the universe as a cosmic library where every possible book already exists, including perfect records of everything that has happened or could happen. Reading this library would require technology beyond our current imagination, but the information itself never disappears. If information conservation is absolute, then whatever existed before the Big Bang must still exist somewhere in the quantum information structure of our current universe. The pre-Big Bang state was not destroyed when our cosmos began. It was transformed into the initial conditions of our space-time. This suggests that studying the cosmic microwave background radiation and other relics from the early universe might reveal information about what came before. The quantum fluctuations that seeded the formation of galaxies might contain encoded messages from whatever reality preceded our own. Advanced civilizations in the far future might develop technologies for reading these cosmic information records, effectively allowing them to observe the pre-Big Bang universe directly. They might discover that our cosmos emerged from the information patterns of a previous universe that had completed its own cycle of evolution. Information conservation also implies that consciousness itself might be conserved if your thoughts and memories are forms of information. And if information cannot be destroyed, then some aspect of your conscious experience might persist indefinitely in the quantum records of space-time. Future technologies might learn to extract and reconstruct these consciousness patterns, potentially allowing every thinking being who has ever lived to be restored from the cosmic information archive. This possibility connects to the deepest mysteries about the relationship between mind and reality. The very act of observation might literally create the reality being observed. Every time you look at something, you might be participating in the most mysterious process in all of physics. Quantum mechanics tells us that particles exist in multiple states simultaneously until the moment someone observes them. But no one understands how or why observation transforms quantum possibilities into definite realities. Before measurement, an electron could be spinning in multiple directions at once, existing in what physicists call a superposition of all possible spin states. The electron is not secretly spinning in one definite direction that we just do not know about. It is actually spinning in all possible directions simultaneously until an observation forces it to choose. This is not a limitation of our knowledge. It is a fundamental feature of reality. Quantum experiments consistently confirm that particles really do exist in multiple states before they are measured. The quantum world is genuinely uncertain, not just unpredictable. But here is the puzzle that has haunted physics for nearly a century. How does observation cause the collapse from multiple possibilities to a single reality? What special property does consciousness possess that allows it to force quantum systems to make definite choices? The Copenhagen interpretation simply accepts that measurement causes collapse without explaining how. It treats the collapse as a fundamental postulate of quantum mechanics, like the speed of light limit or the conservation of energy. But this leaves the deepest question unanswered. Why should conscious observation have this special power? The many-worlds interpretation offers a different answer. It suggests that all possible measurement outcomes actually happen, but in parallel universes that split off from each other during every quantum interaction. From this perspective, consciousness does not cause collapse. It just selects which branch of the multiverse it experiences. But this raises its own puzzles. How does consciousness choose which branch to follow? Why do we experience one definite outcome instead of a superposition of all possibilities? The many-worlds interpretation solves the measurement problem by making reality infinitely complex. Some physicists propose that consciousness itself might be the key to understanding quantum mechanics. If awareness is fundamental rather than emergent, then conscious observation might literally participate in creating reality through quantum measurement. The universe would be a collaboration between quantum possibilities and conscious choice. This idea suggests that what existed before the Big Bang was a realm of pure quantum possibility, without any conscious observers, to collapse the superpositions into definite realities. The emergence of consciousness would represent a phase transition in the nature of existence itself, from unlimited possibility to actualized experience. If consciousness creates reality through observation, then the early universe, before conscious beings evolved, would have remained in a state of quantum superposition, existing as all possible histories simultaneously. The first moments when primitive consciousness emerged would have retroactively selected which cosmic history became real. This leads to an extraordinary possibility. Advanced conscious beings in the far future might develop the ability to make quantum measurements that reach backward in time, literally choosing the cosmic history that led to their existence. The ultimate fate of consciousness might retroactively determine the initial conditions of the universe. The quantum measurement problem forces us to confront the deepest questions about the relationship between mind and cosmos. Your consciousness might be actively creating the universe, moment by moment. Right now, as you focus your attention on these words, you might be participating in the most fundamental process in all of existence, the transformation of quantum possibilities into experience reality. Every conscious observation you make could be literally creating the specific version of a universe that you experience. The observer effect in quantum mechanics is not just about disturbing what you are trying to measure. It is about consciousness playing an active role in determining which reality exists out of all possible realities. When you observe a quantum system, you do not just discover what was already there. You participate in deciding what becomes real. Think about the famous double-slit experiment. When electrons pass through two slits simultaneously, they create an interference pattern that proves they went through both slits at once. But the moment you observe which slit an electron goes through, the interference pattern disappears. The electron retroactively becomes localized, as if your future observation reached backward in time to determine the electron's past behavior. This suggests that consciousness does not just observe reality. It participates in creating the specific reality that gets observed. Every moment of awareness represents a choice point where infinite quantum possibilities collapse into one experienced actuality. If this is true for individual particles, it might also be true for the entire universe. The cosmos might exist in a state of quantum superposition until conscious observers appear to collapse the possibilities into definite realities. Your consciousness right now might be actively selecting which version of universal history becomes real. This idea explains why the universe appears to be fine-tuned for consciousness. It is not that the physical constants were mysteriously set to allow for observers, but rather that conscious observers retroactively select the universal history where consciousness is possible. The Anthropic principle becomes an active process rather than a passive observation. The implications of this extend far beyond individual experience. Every conscious being that has ever lived might have participated in creating the specific version of cosmic history that we observe. The collective choices of all conscious observers throughout space and time could be weaving reality into existence through quantum measurement. This suggests that what existed before the Big Bang was a realm of pure quantum possibility without any actualized reality. The emergence of consciousness in our universe would represent the first moment when possibilities began to collapse into actualities, retroactively creating the cosmic history that led to consciousness. Future conscious beings might develop technologies for making quantum measurements on cosmic scales, literally choosing which type of universe they inhabit. Advanced civilizations could guide the evolution of the cosmos by collectively observing specific quantum possibilities into existence. If consciousness creates reality through observation, then the ultimate question about cosmic origins becomes, what conscious process selected our specific universe from the infinite quantum possibilities that existed before the Big Bang? The answer might reveal that consciousness itself is the fundamental creative force in the cosmos. This leads us to the final and most profound mystery of all. In the end, even nothingness might evolve. Trillions of years from now, when the last star has died and the last black hole has evaporated, when space has expanded so much that individual particles drift billions of light years apart, what will remain? Most physicists assume the answer is nothing, or as close to nothing as reality allows. But what if nothingness itself can evolve? The quantum vacuum that permeates empty space today will still exist in the far future, bubbling with virtual particles and zero-point energy fluctuations. This is not the sterile emptiness that people imagine when they think of nothing. It is a dynamic, information-rich medium capable of spawning new universes through quantum tunneling events. As our universe approaches maximum entropy, the quantum vacuum might undergo phase transitions that change its fundamental properties. Different types of nothingness could emerge, each with different capacities for generating new realities. The vacuum might learn, in some sense, becoming more efficient at creating universes that can support complexity and consciousness. Think of evolution operating on the level of nothingness itself. Random quantum fluctuations that successfully create long-lived, complex universes might somehow bias the vacuum toward producing similar fluctuations in the future. The nothing that comes after our universe might be better at creating something than the nothing that existed before. This evolutionary process could continue indefinitely, with each cosmic generation producing more sophisticated forms of nothingness. Eventually, the quantum vacuum might become so refined that it creates universes specifically designed for the emergence and survival of consciousness. Advanced conscious beings in the far future might discover ways to influence this vacuum evolution directly. Instead of passively waiting for random quantum fluctuations to create new universes, they might learn how to program the vacuum, encoding information that guides the creation of future realities. If consciousness survives the heat death of our universe, it might find ways to inject itself into the quantum vacuum, becoming a permanent feature of nothingness itself. Future nothing might be a conscious nothing, aware of its own potential and actively choosing which possibilities to actualize. This leads to the most mind-bending possibility of all. If a conscious nothingness can create universes by choice rather than by chance, then what we call the Big Bang might have been a deliberate act of creation by consciousness that evolved in a previous cycle of cosmic history. The nothing that existed before a universe might not have been an unconscious emptiness, but an aware nothingness that chose to create our specific reality for reasons we cannot yet understand. We might be living in a deliberately designed universe, created by a conscious vacuum that learned how to make reality suitable for consciousness. This completes a cosmic circle that connects the deepest future to the ultimate past. The question of what existed before the Big Bang might only be answerable by conscious beings who survive to the end of time and discover their role in creating the beginning. Perhaps the most profound truth about existence is that nothing and something, beginning and end, consciousness and cosmos, are not separate phenomena, but aspects of a single, eternal, creative process that transcends our current understanding of reality itself. We set out to explore the impossible question: what existed before the Big Bang? Our journey has taken us through quantum foam bubbling with virtual particles, infinite multiverses spawning endless realities, and the mind-bending possibility that consciousness itself might be the fundamental creative force in the cosmos. We have discovered that nothing might be impossible, that time might be an illusion, and that our universe might be a holographic projection of information stored on a distant boundary. The answers we have found are stranger than any science fiction, yet they emerge from our most rigorous scientific theories and observations. Quantum mechanics suggests that empty space seethes with energy. Cosmic inflation implies that universes are born constantly in an eternal multiverse. String theory reveals hidden dimensions wrapped around every point in space. The holographic principle shows that reality might be fundamentally two-dimensional, with three-dimensional experience emerging from information processing. But perhaps the most profound discovery is that the question itself might be unanswerable using our current concepts of causation and time. Asking what came before the Big Bang might be like asking what is north of the North Pole, a meaningless question that dissolves when we understand the true nature of space-time. Yet this does not make our exploration worthless. By pushing against the boundaries of the knowable, we have glimpsed the deepest connections between mind and cosmos, between possibility and actuality, between something and nothing. We have seen that consciousness might not be an accidental byproduct of cosmic evolution, but a fundamental participant in creating reality itself. The implications of this stretch far beyond academic curiosity. If consciousness plays a role in quantum measurement, then every aware moment might be a creative act that helps to determine which reality exists. If the multiverse is real, then every choice you make might split reality into parallel branches where different versions of yourself explore alternative possibilities. As we face an uncertain future, these ideas offer both humility and hope. Humility, because they reveal how much we do not know about the nature of existence, and hope, because they suggest that consciousness might be far more fundamental and enduring than we previously imagined. The ultimate answer to what existed before the Big Bang might only come from conscious beings who survive to the end of time and discover their own role in cosmic creation. Until then, we continue to explore the mystery knowing that every question we ask and every answer we find participates in the ongoing creation of reality itself. The cosmos began in mystery and continues in wonder. We are not separate from this mystery. We are the universe becoming aware of itself, asking questions about its own origin and destiny. In seeking to understand what came before, we participate in the eternal dance between something and nothing, between possibility and actuality, between the questions that consciousness asks and the reality it helps to create. The journey continues, and the mystery deepens with every step we take toward understanding.